So in this session, we will discuss the effect of friction in nozzles. So this is one topic of the module number 5, that is steam nozzles. Okay. So to understand the effect of friction in the nozzles, you need to remember the two important points. The point number one is when the fluid, that is steam, passes through the nozzles, expansion takes place. So what type of expansion it is? It is a reversible adiabatic expansion process. Reversible adiabatic expansion process is also called isentropic process. That is, entropy during the process remains constant. So this process is ideal case. If the entropy is constant during the process, it is ideal case. Here friction is not considered. But in the actual expansion through nozzles, so friction factor come into the picture. So due to presence of friction, the expansion process will not be reversible, it will become irreversible. When the process is irreversible, then it is called non-isentropic flow. So here we have written it is due to the presence of friction between the fluid and the surface of the nozzle, or friction may be between the two molecules of the fluid itself. That is also a point. Okay, now to understand the effect of friction better, so we will consider a convergent divergent nozzle. So here I have taken one convergent divergent nozzle. So point number one is inlet through which the steam enters inside the nozzle, and point number two is called the intermediate point, that is throat section. What is throat? Throat is the minimum area of the, or minimum portion or small portion of the nozzle is called throat. And point number three is outlet. P1, P2, P3 are pressure at point number 1, 2 and 3 respectively. And similarly H1 and H2, H3 are the enthalpy at point number 1, 2 and 3 respectively. Here first part is convergent nozzle, I have represented here, and the second part is throat, and the third part is divergent nozzle. The convergent nozzle, the divergent nozzle is insulated so that heat exchange between the system, that is nozzle, and the surrounding is equal to 0 through entire nozzle. Okay, so entire parts are, throughout part it is insulated, so value of Q is equal to 0 here. So now we will take high pressure, okay, high temperature superheated steam enters into the nozzle. Okay, so here it is high expansion takes place. So due to expansion, enthalpy drops. H1 is enthalpy at inlet, H2 is enthalpy at throat. So H1 is greater than H2. So due to expansion, enthalpy decreases. So H2 will be lesser than H1, and same process we have represented in HS diagram here. So point number one is here. Point number two, it is expansion takes place. Okay, so what type of process is 1 to 2? It is isentropic. Now the question comes, why it is isentropic? Why it is reversible adiabatic process? Why you are not considered the friction factor in the convergent nozzle? The reason is, if you observe carefully, the length of the convergent nozzle is less than the length of divergent nozzle. Okay, so here it has small length. So when the convergent nozzle length is small, the friction is small, the friction is less compared to the divergent. So the friction factor in the convergent nozzle is neglected. So when you are neglected friction, it will become an ideal expansion process. Ideal expansion process is nothing but isentropic process. Isentropic process, here entropy remains constant. So we'll represent it by vertical line in the HS diagram. That is the reason see here 1 to 2 is exactly straight vertical line. So entropy is constant. S1 is equal to S2 here. But When the steam uh, touches the point number 2, here it will become dry steam. It will not be superheated steam. The reason is, at point number 1 it is superheated, that is high pressure is there, high temperature is there, and superheated steam. So due to expansion between 1 and 2, the superheated steam will become the dry steam. The value of x will be equal to 1 at point number 2. So that is the reason point number 2 is located on the dry saturated line. Okay, so in the HS diagram, so this thick line indicates it is dry saturated line. So if any point on this line, then the quality of steam is 100%, that is dry. Okay, so if any point above this curve, that is superheated region. That is point number 1 is superheated at pressure P1. So here we have same thing represented in the HS diagram. So due to expansion in the convergent nozzle, the superheated steam will become dry steam. The same point is represented here. Now the expansion of the steam still continues in the divergent part. Okay, so in the divergent part, the length of the divergent nozzle is more, and obviously the friction will be more. The friction between the steam and the surface of the nozzle. Assume that here the steam is flowing through the divergent part. The steam is coming outside. So this dotted lines indicates the steam flow. The friction between this steam and inside surface of the nozzle. So due to friction, the heat will be generated, it is Q, and this heat will not go outside. Okay, there is no question of going outside because it is insulated. Q is equal to 0. You have restricted the flow of heat from system to the surrounding. You have insulated. So that heat will add heat to the steam itself. So whatever the steam which is coming from the throat, okay, throat section, there is a dry steam. So whatever the heat generated or produced due to friction between the steam and the inside surface of the nozzle, that heat will not go outside because it is insulated. So that heat will be within the system only. And that heat is added energy to the steam presented in the divergent nozzle. So due to the addition of heat, the enthalpy increases. So H2 and H3, if you consider H2 and H3, so H2 to H3, the enthalpy increases. If you consider friction, if the friction is not considered, then H2 will be more than H3. Are you able to understand the point clearly? Yes. If you consider the friction factor inside the surface of the nozzle and the steam, so due to friction, heat generates. That heat is not going outside because it is insulated. So the heat will be within the system only. The heat is added to the steam only. So due to addition of heat to the steam, the enthalpy increases. Understood? What is enthalpy? Enthalpy is the energy content in the steam. If you supplied some amount of heat to the steam, the enthalpy increases. Understood? If the heat is rejected from the steam, enthalpy decreases. Understood? Here, so point number 2 to 3, so vertically I have represented 2 to 3, that is isentropic flow. If the expansion process is exactly vertical, then it is isentropic flow, that is friction is not considered. But due to presence of friction inside a divergent nozzle, the enthalpy increases. For example, see here, point number 3 is here. So due to friction, the enthalpy is increases from 3 to 3 dash. So here point number 3, H3 is here, and H3 dash is here. H3 dash is the enthalpy due to friction. So this dotted line indicates the actual expansion of steam in the nozzle. Understood? So 2 to 3 dash is actual expansion process in the nozzle, and 2 to 3 is ideal expansion process. So ideal expansion is isentropic, and actual expansion, that is 2 to 3 dash, is non-isentropic process, that is irreversible adiabatic. So due to the factor of friction, the enthalpy increases. That is one point. The second point is, just you observe the curves, the dotted lines here. Here the thicker line is a dry saturated line, that is x is equal to 1. What does it mean? 100% steam. There is no water particles. Just you take one more curve just below this thick line, this thick curve line. So one more curve I have taken below the dry saturated line. I have represented x is equal to 0.9. What does it mean? 90% steam, remaining 10% water. So similarly, you take three curves just below the dry saturated line. So you take one more curve, it is on point number 3 here. So this last dotted lines curve. So this is x3, point number 3. Just at the same time, you draw one more dotted line at point number 3 dash. Okay. Here, just you observe these two dotted curves. The value of x3 dash is more, or value of x3 is more? Obviously, x3 dash is more. X3 dash is above x3. So from here, if you are going towards the dry saturated line, the quality of steam increases. Here x3 is approximately maybe zero point 0.7. Okay, zero point 0.7, that is 70% steam and remaining 30% water at point number 3. But 3 dash is just ahead of point number 3, and the value of x3 dash may be 0.75. So due to addition of heat generated by the friction, not only increase the enthalpy, it also increases the dryness fraction of the steam, because you are adding heat. For example, let us consider the temperature of the steam in the diverging nozzle is 210 degrees Celsius, approximately 210 degrees Celsius. So due to friction, the heat Q generates, correct? So that Q is adding heat to the steam, and the temperature of the steam is increases. So 210 degrees Celsius steam will become 250 degrees Celsius steam. So 210 degrees Celsius quality of the steam is less, and 250 degrees Celsius temperature steam quality is better than 210 degree. So by addition of heat that is generated by the friction between the fluid and the surface of the nozzle, increases the quality of the steam also. Understood? It is very important. This question may ask in the gate exams, some interview questions. Understood? So the quality of steam also increased, and the enthalpy of the steam also increased. That is the effect of friction in the nozzle. See here, I have written here H3 dash is more than H3. And at the same time, here X1 is equal to 1, that is purely superheated steam, and X2 is also equal to 1, that is, it is point number 2 is on dry saturated line. Why you are represented with vertical straight line is, the reason is, in the convergent nozzle friction will be there, but the friction is neglected. Why it is neglected? It is convergent nozzle has a small length. Okay, so shorter in length. So the length of this convergent nozzle is less than the divergent. The friction compared to divergent nozzle, here the friction is less, so it is neglected. So when the friction is neglected, obviously it will become an ideal case, ideal expansion process. So ideal is nothing but isentropic expansion. That is the reason I have not represented with 1 2 with the dotted lines. So if you represent 1 2 dash, then it will become actual case, but we have not done it. Okay. Similarly, x3 x3 is less than 1 because point number 3 is below the dry saturated line. If any point below the dry saturated is wet steam. Understood? Okay. So here, refer figure A, the convergent portion of the nozzle is smaller than the divergent portion. The friction between the wall and the fluid stream is small as compared to the divergent portion. So thus, most of the friction occurs in the divergent portion because length of the divergent is more, is represented in the HS diagram. This is what I explained here. So next, so due to the friction in the nozzle, the enthalpy drop decreases. Some students will become confused. Just before 10 seconds, sir has told enthalpy increases. 100% enthalpy increases, but here it is enthalpy drop. Enthalpy drop is nothing but difference in enthalpy. For example, we'll go to HS diagram. Okay, you now you consider total expansion from point number 1 to point number 3. Observe carefully. Point number 1 is here, point number 3 is here. So h1 minus h3, that is one value. Keep in your mind one value, some value x. So h1 minus h3, that is x value. h1 minus h3 dash, that is y value. So which value is more? h1 minus h3, that is x value is more compared to h1 minus h3 dash, that is y value. So enthalpy drop decreases. X is more, y is less. So enthalpy drop decreases, but the final enthalpy increases. If you okay, that is the reason we have written here enthalpy drop decreases, and at the same time entropy increases. See here, entropy at point number 3 is S3. The horizontal line indicates entropy, that is S. S3 is here, S3 dash is here. Okay, so S3 dash is more than S3. Understood? So entropy increases, enthalpy increases, entropy also increases, but and quality of steam also increases, but enthalpy drop decreases. Okay, next, here the same process what I explained is written here for your exam point of view. So there is no isentropic loss between 1 and 2 because we are not considered friction since it is small length conversion portion, but from 2 to 3 dash is actual adiabatic expansion process, and 2 to 3 is reversible isentropic process. 2 to 3 is reversible, but 2 to 3 dash is irreversible, that is actual. This is ideal case. So the last we will conclude, we will summarize. So what is the effect of friction in the nozzle is, so reduction in enthalpy drop, that is difference between enthalpy drop is decreases. But if they ask you in other way, effect of friction increases the enthalpy at the outlet of the nozzle or decreases the enthalpy at the outlet of the nozzle. So at compared to isentropic and actual process, in the isentropic the value of h3 is enthalpy is at point number 3 is h3, but due to friction actual expansion the point number 3 will move to 3 dash. So due to friction enthalpy increases. Okay, it is compared to only isentropic. And second point is important, reheating of the fluid. As I told you, so considering the friction, heat generates, and the generated heat will not go outside because the nozzle is insulated. Okay, so the heat will be within the system. That heat is adding or increasing the temperature of the steam. So it is called reheating of fluid. So point number 3 is decrease in mass flow rate. Obviously, the mass flow rate of the steam decreases, and reduction in exit velocity of the fluid, and finally increase in specific volume. So these are the 5 factors or effects takes place uh, by considering friction in a nozzle. Okay, So nozzle efficiency is defined as, that is, actual enthalpy drop to the isentropic enthalpy drop. So this equation will be used for solving efficiency of the nozzle in the numericals. So actual enthalpy drop is what? Actual enthalpy drop is H1 minus H3 dash. Okay, and isentropic enthalpy drop is H1 minus H3. There should small mistakes here. H1 minus H3 dash, it should be H3 dash, and it should be H3. Okay, so here H1, H3 and H3 dash are the unknown to calculate nozzle efficiency. So these three enthalpies values will be taken from steam table at the desired pressure and temperature. Okay, or else you can take these three enthalpy values using HS diagram, Mollier chart diagram. So if you have any doubts on this effects of nozzle, effects of friction in the nozzle, you can comment and you can ask doubts in the comment box. So thank you so much for watching this video. So in the next lecture uh, session, we will derive one important derivation, that is discharge through the nozzle, or it is also called derive an expression for critical pressure ratio. That is very, very important for exam point of view. Okay, thank you so much for watching this video.